Hello dear students, today we'll discuss the one more interesting topic, that is of spring block system. In earlier classes we have discussed the acceleration, velocity, acceleration graph, velocity graph, displacement graph of the body or the particle executing the simple harmonic motion with the respect to their graph, how to plot it, and if graph is given, how to identify the acceleration. These all things we have already discussed. So based on that, very important concept is that spring block system, that these things we have already learned in a previous chapter, that is of restoring force. If same concept is allowed here, if the spring is here, loaded spring it is, so that is also executing the oscillation, then it executes the simple harmonic motion or not, what kind of a time period you are getting, that is we are going to discuss here. If the load is attached to that spring, so this is the spring here, it is attached to the one rigid body. If load is attached to the spring here, it displaces slightly from its mean position. That means this is the right now mean position, thus it slightly displaces from its mean position, then releases. When releases, then it load performs the simple harmonic motion. Now let us go ahead with the extended part here. If the spring is there here, right, so spring is there here, so just displaced here from here to here it is. So once stretch it here for the displacement, means you are allowing the it's to be in the extend from the mean position. So this is the mean position, this is a displaced at the certain distance x it is, and this force is there here, force is acting on that body, but it is moving backward here, that is nothing but the restoring force it is, that also we have discussed, that is experiencing the simple harmonic motion it is. What is simple harmonic motion? F is equal to minus kx it is. So it's stretched here, stretched in the sense it is displaced from its mean position and released. So it once it is released, it want to try to come back to its original mean position, that is it's coming back, force is towards the backward direction. So this is the displaced position here, this, so body displaced to the right to the small displacement x, restoring force produces in the spring here. So restoring force is produces in the spring, that is F is equal to minus kx, where a negative sign indicates what here, force and the displacement are their opposite direction. See, look at here, displacement is taking in this part, right, force is in the opposite direction, so that's why negative sign comes here. So it is experiencing coming back, front back, so it is experiencing the simple harmonic motion. This was the statement it is given. As we have F is equal to mass into acceleration here, acceleration of the block is nothing but the instantaneous acceleration it is. Instantaneous means spontaneously it is getting that force it is, right? So when you compare this force and the body executing the simple harmonic force here, so what you are getting, ma is equal to minus kx it is, right? So where we can say acceleration is equal to k by m minus k by mx here. So it is nothing but the omega square x. So this is acceleration of a particle executing the simple harmonic motion it is. So acceleration of a particle experiences the simple harmonic motion here, as we can write omega square is equal to k by m here, omega is equal to root of k by m here. But angular frequency omega is equal to nothing but 2 pi f it is. So 2 pi f. So where we can write it here, 2 pi f means it is an angular frequency, means reverse part of the time period it is. Now we are getting f is equal to what here, 1 by t, means how much time it will take to complete the oscillation. So time period for to complete the one oscillations. If you go ahead with this, omega is equal to 2 pi by t it is, right? So now we are getting time period, that is compare with this part. So omega is equal to 2 pi f here, 2 pi omega we are getting root of k by m here. So 2 pi 1 by t here. So the time required, how much time required here, that is of 2 pi root of m by k. Directly I have written. So you can just take it the part of t is equal to 1 by t is equal to 1 by 2 pi root of k by m it is. So directly I have taken the time period t is equal to 2 pi root of m by k it is. So this is the time period required for the particle to execute the simple harmonic motion. So this is about the block. When the block is attached to that spring here, when spring is displaced from its mean position, same time period is experiencing what the time period it is experienced by the particle, already it is in a simple harmonic motion. So this is one case. If the spring is connected in the form of parallel, means motion of a block attached to the two springs. So motion of the block attached to the two spring here. So if you go ahead with the two spring with the same block, if you attach to the two spring here, right, of the same mass, so this is the nothing but the mean position here. Once displacement is taking place from the mean position here, so once displacement is taking from the mean position, certain distance here for the same load here. So that is of, we can say this is a 1, this is a 1 spring here, K2. So this is a displaced position here. So this displaced for both the spring it is a same, but body is also same here. Now this what kind of a time period it is experienced by the block, we have to cross check, where x is nothing but the displacement of a block, restoring force is produced. So that is force is acting here. If you just stretch is displaced here from the mean position, released it. So once it is released, it is a moving backward direction, means displacement is there in this direction, force is there in this direction. So it is experiencing the simple harmonic motion. So you just imagine here, if you released it here by extending the spring, certain distance it is expanding here. Once you release that, releasing in the form of applied force should be removed. That force is opposite to the direction of displacement, means it is trying to come back to its mean position where it has started the motion here. So that is of mean position. That's why you are getting negative sign, that you know it. It is restoring force is produced in the spring. The two springs are in parallel it is. So that two springs are in parallel. So what kind of force you are getting here? F1 is equal to minus K1x here. F2 is equal to minus K2x here. So two forces, because two forces are there, but displaced part of the body is same it is. Displaced part of the body is same from the mean position. What is the net force? Net force means what? Net restoring force acting on the body here. That is F net is equal to F1 plus F2. Both the forces are restoring forces. Now we are getting minus F1 is what here? Minus K1 minus K2x. So I am getting minus, taking outside K1 plus K2 here. Right? Minus K1 and K2 here. I am writing minus KPx here. So F is equal to minus KPx. That means it is of effective spring constant or the force constant, where we can say K is nothing but the spring constant. But in this case, K may vary in the sense, now we are taking it as a spring here. So we are called it as it is a spring constant. If you take the different form, next in upcoming classes it is coming, what will be the restoring force of the liquid, what will be the restoring force of the other particle when it is depressed. So these at that time K will be different. So here we are taking the spring here, that's why it is a K is a spring constant, that to effective spring constant, because two springs are attached in the form of parallelly here, parallel combination. Now we'll go ahead with the part of completioning or finding the time period, which is the time period is the same as the time period of particle executing the simple harmonic motion here. Now t is equal to 2 pi root of m by kp. We can write now directly. We have time period is equal to 2 pi by root of m by k. So in place of k, I am writing here effective spring constant k, p here. So that is of 2 pi root of m by k1 plus k2 here. So k1 plus k2, that means this is the time period. If you go ahead with the frequency, what is happening here? 1 by t, that is 1 by t means nothing but the 2 pi of root of k1 plus k2 divided by m. So this is the frequency. So and the time period, both will experiences the same simple harmonic motion here. So that means it is possible for the body attached to the parallel combination of a spring also and the load attached to the spring also. Now let us move on to the series combination of a spring here. So what kind of experiences, whether that is also same as the simple harmonic motion or not. Now when we go ahead with the vertical part here, vertical combination of spring here, so m is there, this is the mean position here right now. Once you stretch it for the or displaced here, you can able to take, so displaced part, I'm going to write it here x here. This is the mean position, I'm writing it as mean position as I here. So this is a displaced part here, displaced position here, right? Displaced position here. First we'll understand this vertical part, next we'll connect it in series here. So this is a expanding part, this is the mean here, this is the displaced part here. So it is balancing by its own weight. So tension is also developing on the opposite direction here. Now let us make it in the form of series combination, means two springs are attached here for the load, right? So let me go ahead with the k1 and k2 here. Now displaced certain distance here, so certain distance from here, right? So here also connected is the displaced part, it is, this is the mean position here. So once it is moving in the certain distance, when you take it into the horizontal part, so what kind of imagine you are getting, that is, so k1 it is, k2 it is load. So displaced part it is k1, k2 here, so this is the mean position, this is a displaced position, where we can say x1 here, where we can say x2 here, the complete displacement is x here. So that is of body here. So where x1 and x2 are the time to displacement, x1 and x2 are the two displacement, then the restoring force produced in the springs are constant force, it is, because it is moving back. Restoring force is moving back. If kx is an effective spring constant, kx means what here, that is of in series combination. So that is of a series combination of a spring here, that is nothing but the effective spring constant, then it is a series combination. Then the restoring force F is equal to minus kx it is. So in place of k, I am writing here kx because it is a series combination of the spring here. Now I can write it x is equal to F by kx it is. So net displacement is given by, what is the net displacement? X is equal to x1 plus x2. Here in the parallel combination we have taken net force acting on it. Here it is the net displacement acting on it. So next, net force and net displacement, how it is going to be vary, that only we are going to discussing here. In the parallel combination, we have got the net force acting on it because both are on the same form, but here it is in the series combination. So x is equal to F by kx it is. Now net force also we got it here, that is of x1 plus x2 here, that is of total displaced form. So now this x is F by kx it is. X1 is what here? F by k1, F by k2. We can write no here. This is a force experience. So 1 by kx is equal to 1 by k1 plus 1 by k2 here. So we can write it here, kx is equal to k1 k2 by k1 plus k2 here. So total time period we have 2 pi by root of m by k it is. In place of k, you can just substitute this form. We'll get the series combination of a spring attached to the body or a particle executing the simple harmonic motion. So 2 pi root of m by kx it is. So 2 pi of root of m by k1 plus k2, k1 k2, k1 plus k2 here. So it will come up, remains with what here? Root of m k1 plus k2 divided by k1 into k2 here. So k1 into, this is the time period of the block of a series combination of the spring here. So this is also experiences the same as a simple harmonic motion. It is same as a simple harmonic motion it is. So by this we can conclude that whatever may be the body which is attached to that, which is experiences the simple harmonic motion, either the spring, single spring which is displaced certain mean position here, it is try to come back to its original position, mean position it is. When you same kind of a spring attached in the form of parallel also, same kind of spring it is attached to the series combination also. Whatever may be the combination of a spring which has a greater simple harmonic motion, you can just compare this part here. If spring has a too much tight, it has a lesser time period. Tight in the sense it is very difficult to exhibit the simple harmonic motion. At that time period is very less it is. It will take a very fast simple harmonic motion. If mass of the body is more, time period is slow. If mass of the body is less, time period is less. So it is a direct, time period is directly proportional to mass. How mass increases, time increases. How mass decreases, time decreases. So time period is direct inversely proportional to the stiffness of the spring here. How stiffness of the spring is there, time period is reverse of it. Means it takes the less time period to complete the simple harmonic motion. If tight spring is less, very loose it is, so it will takes the loose in the sense it is restoring force is nothing but a very fast it is. That time period is very less, very short only it will complete the oscillation. So this is about the time period of the spring block when it is connected in a series and parallel combination. Now we'll discuss the same things in the simple pendulum. So simple pendulum experiment you might have been done in your own in the laboratory form here, right? So we'll discuss that simple pendulum here. If it is a rigid body, just recall what we did here. This is of mean position. As we can say, this is x is equal to 0. It will reach to the extreme position. Simple pendulum means we have to take it in this form, right? So if you just to draw the suspension point to the suspension point of diagram here, right? This is nothing but the point of suspension. The length of the thread you are going to measure and kept it on the rigid body which is attached to the stand here, where it has to exhibit the simple harmonic motion. So this is the mean position. So this point starts oscillating here. So oscillation, right, about a simple harmonic motion it is. So it is exhibiting. Now look at here. If this part is starting to the next extreme position here, right, so it is going to be resolved into two components. Two components in the sense, before going to that, let us take tension is developed here. When it is moving here in this part, it will take it into the part where body is going to be balance its own weight here. So the body is going to be balanced with its own weight here, where we'll get the two resolving into two component here. So what are those? These are nothing but the mg cos theta and mg sin theta here. What is this? These are the forces which is experiencing on the body, which is already in the pendulum form. Pendulum form means it is already in the form of simple harmonic motion. But mg cos theta is a one force which is balanced by the tension developed on the point of suspension of a particle here. So this is the point of suspension where we are getting body is starts to oscillation here. So I will call it as this is tension A. So once it is balanced by the tension here, then it is not responsible to make it as a oscillation. Which part is responsible to make a body to come back to its original position and next to the extreme position, that is of mg sin theta. So look at here, force is there, right? Force is resolved into two components and this part is balanced by the tension developed on the suspension, point of suspension here, and mg sin theta is moving in the mean position, towards the mean position, means it is opposite to the displacement. Force is there here, this is of displacement. So I can write it here, mg sin theta is responsible to create the restoring force for the bob towards the mean position. So I can write it F is equal to minus mg sin theta here. So sin theta, see here also theta it is. Here also theta, the same form it is coming here. So F is equal to sin theta, where we can write weight is equal to mg resolved into two components, that is of balanced by the mg cos theta is a tension here, unbalanced also we can say that is of mg sin theta. There is no other force to be balanced this force, so that it has to be get cancelled, which is not acting as a, or which will not plays the role of friction here. This is not a friction, this is of restoring, it is coming back to original path it is. So this brings the restoring force which brings the bob to its mean position. So restoring force F is equal to mg sin theta. You might have understood here negative sign indicates it as force and the displacement are opposite in direction here. But we have force is equal to m into A by the Newton's law. Compare here, MA is equal to mg sin theta, which is a restoring force here. So mg sin theta, sorry, minus mg sin theta here, because it is opposite in direction, force and displacement. M and M get cancels here. Acceleration is equal to minus g sin theta. So where theta is a very small, sin theta is very small, so we can take it as a theta here, as we are getting acceleration is equal to minus g theta here, minus g theta. From the simple pendulum, this form it is diagrammatical form, we are getting theta is equal to, so you can take either this theta or this theta here, right? So theta is equal to x, this is x, no, opposite upon adjacent, opposite upon adjacent. We can take a slope also, that is tan theta will take no same here also, theta is equal to x by l. Substitute here, a is equal to minus g into x by l it is. So look at here, a is equal to minus g by l x it is, where g by l is a constant, only acceleration is depending upon the displacement x. So we are taking g by l is a constant, it is g by l is a constant here, then x acceleration is directly proportional to x it is. So acceleration of a bob of a pendulum is directly proportional to its displacement, and the direction of acceleration is opposite to the direction of its displacement. Always it is. So body is moving in this direction means acceleration means nothing but the force it is. So that is directed towards the mean position, opposite to the direction its displacement here. But acceleration executing by the particle means it experiences that it depending upon the displacement here. So depends on displacement, opposite in displacement. This is happening in the acceleration of the bob here. So we have to check whether the time period is same as what we are getting in the simple harmonic motion. So we have acceleration is equal to minus omega square x in simple harmonic motion here. That is acceleration of a particle in simple harmonic motion it is. So we have acceleration is minus g by L of x it is. That means omega square is equal to omega square x is equal to minus g by L of x. So x get cancels, minus also get cancels here. So g by L here, omega square. So omega is equal to root of g by L it is. So root of g by L. Then this omega is a 2 pi by t it is again. That is a root of g by L here. Time period t is equal to 2 pi of L by g it is. So this is the time period of the pendulum which experiences the simple harmonic motion here. That is the pendulum form of the bob also experiences the to and fro motion here. From mean position to extreme position to mean to next extreme to mean. So this completes the oscillation. Like that it is continuous process is taking place. Once you compared with the second pendulum in the sense what here, how many seconds it will take to complete the oscillations. So that's why it is called as a seconds pendulum. So we know that 2 seconds it will take to complete the oscillation here. Now we'll cross check seconds pendulum. So seconds pendulum, time period we have that is of 2 pi root of L by g it is. So squaring on both the sides. If you go ahead with the squaring on both the sides here, we'll get to know that whether it is seconds pendulum or not. So 2 pi square root of L by g whole square it is. So that is of 4 pi square root of L by, root will get cancels, no, square and root. So that is of L by g it is. That is of t square. Next, L we are getting that is of g t square by 4 pi square it is. L is what here? Length of the thread which is used in calculationing of the seconds pendulum here. So where g is equal to 9.8 meter per second square, t is we know that 2 seconds to complete the one oscillation. Now we'll get to know that what length should be prescribed which is exhibiting the simple harmonic motion, or the 2 seconds to complete the one oscillation. So put the value here, g is 9.8, t is of 2 seconds square, 2 square here, then 4 into 3.142 square it is. So almost we are getting L is equal to 1 meter. So length of 1 meter wire or a string thread which experiences the simple harmonic motion, it will take a 2 seconds to complete the one oscillation here. So that is the meaning is simple pendulum here. So this is about the how it is experiences the simple pendulum form, seconds pendulum form, and the another form that is of spring block system, parallel combination, and the series combination, how it is experiences the simple harmonic motions. These all things we have already discussed. The thing is that we should remember how many time form we are getting for the series combination, for the parallel combination of a spring. It is displaced for the mean position to the certain extent position here. What is happened, and another form that is of a parallel combination. So how it is a time, in all these cases we are getting the time period which is the same equivalent as a particle executing in a simple harmonic motion it is. So that means it's all holds good. Only thing that where the particle is executing the simple harmonic motion, as we compared the discussion, its kinetic energy and the potential energy, the maximum and the minimum, it is compared, those are not the simple harmonic motion. That means these concepts are discussed in simple harmonic motion, but they are not following any equation, as we have discussed x is equal to a sin omega t, which is moving from mean position to extreme position. As it is a moving from extreme position to mean position, we have equation that is of x is equal to a cos omega t. These all acceleration form, velocity form is not accepting by the particle, where it is all having the kinetic energy and potential energy. Through a graph also we can recognize how it is coming, maximum minimum, maximum minimum. It is not going the positive extreme, it is not going negative extreme. That is one case. And the second case, it is not showing the extreme position to mean position, mean position to extreme position. It is just moving from maximum to minimum, maximum to minimum, 0 to maximum, or maximum to 0. That's it. It's not depending upon the negative extreme or the positive extreme. So that positive and negative extremes only decides the particle executes the simple harmonic motion or not. A particle experiences the periodic motion, means after a certain fixed time or a certain time interval, it will reach to the same position. So that we know, we have already discussed in the first class only differences between the oscillatory motion and the differences between the periodic motion. Simple harmonic motions behaves like a periodic, but it has a different nature, that is of to and fro motion. So that is not possible only in the form of kinetic energy and the potential energy. The remaining part, remaining things, everything will accept the simple harmonic motion. In case of spring also it is accepted, and in case of a simple pendulum, in the discussion of seconds pendulum also it is accepted. That means simple harmonic motion itself is a very wonderful experience, as we have studied in the detailed part. So in the next class we are going to discuss the very important part, that is oscillations in the U tube and the floating body, and the remaining concept we are going to discuss here.